Okay, let's dive into this. Welcome to today's explainer, where we're going to crack open the ultimate cosmic rulebook. When we look up at the night sky, it looks so peaceful, right? Almost static. But in reality, space is this incredibly dynamic, extremely fast-paced environment, and it is governed by some absolutely strict, undeniable laws of physics. So today, we're going to break down exactly what those rules are, specifically focusing on gravity and speed. And then, we're going to look at one of the most fascinating, true detective-style stories in the history of science, where these very rules were used to hunt down a missing planet hiding in the dark. It's a pretty fundamental question, isn't it? I mean, we are literally hurtling through the void at terrifying speeds right now. Yet we never just drift off into the abyss. We stay locked in this perfect, continuous loop year after year after year. So why? Well, to understand movement in space, we first have to understand the invisible tether that holds the whole shebang together. There is a single, dominant boss in our solar system keeping us all in line, and that force is gravity. To really wrap our heads around this, just look at this comparison. Down here on Earth, the strength of gravity pulling you down to your chair right now is 10 newtons per kilogram. That's what gives us our weight. But the sun's gravity, oh man, it is a staggering 270 newtons per kilogram. That is exactly 27 times stronger than what we experience here. It's this immense, totally overpowering gravitational pull that reaches out across millions and millions of miles to act as the ultimate glue for our entire solar system. And the reason the sun has such a tremendous grip on us comes down to one really simple rule. Objects with more mass just have more gravity. And the scale we're talking about here is almost hard to fathom. The mass of the sun is 330,000 times greater than the Earth. In fact, if you took every other planet in our solar system and smashed them all together, the sun's mass would still absolutely dwarf them. So it's not just a bright light in the sky, it is an unimaginably heavy anchor. And this brilliantly illustrates how that anchor actually works in practice. If you roll a ball, it naturally just wants to travel in a straight line, right? Well, planets are exactly the same. Left to their own devices, they want to fly off in a straight line directly into deep space. But the force of gravity from the sun is constantly acting inwards, continuously pulling the planet toward the center. This non-stop inward pull bends that straight line into a curve, giving us an almost perfectly circular orbit. So, that explains the path we take, but what about the speed? Why do planets keep moving for billions of years without ever slowing down? On Earth, movement requires constant energy. I mean, an airplane wing is literally designed to push against particles in the air. That creates air resistance, which acts in the opposite direction to slow the plane down. But look over at the Juno space probe. In space, movement is an entirely different ballgame because, well, there's absolutely nothing to push against. And that's because space is a vacuum. Since it's a completely empty space with no particles floating around, there is zero air resistance, zero friction. It totally removes the brakes that we are so used to having here on Earth. Because planets are moving in a vacuum, there's just nothing out there to slow them down. The only force acting on them at all is gravity. And because there are no brakes in space, the speeds objects can reach are just mind-blowing. Just look at this number. 266,000 kilometers per hour. That is the record-breaking speed the Juno probe reached when it passed Jupiter back in July 2016. It made it the fastest object humans had ever made. Achieving a speed like that on Earth is literally impossible. The air resistance would tear any ship to shreds in seconds. But in the vacuum of space, once you get going, you just keep going. Now, what's really interesting about this slide is how all of this creates a totally clear trend in planetary speeds. We know the sun's gravity dictates everything, but that gravity obviously gets weaker the further away you get. Take a look at the data here. Mercury is absolutely zooming around at 48 kilometers per second. Earth is sitting at 30, but by the time you get way out to Neptune, it's a sluggish 5 kilometers per second. So we have this direct, undeniable mathematical relationship. As the distance from the sun increases, the speed of the orbit decreases. To put this into perspective and really cement this rule, Mercury is the closest planet to the sun, which means it feels the absolute strongest gravitational pull. To avoid getting sucked right into the sun and incinerated, it has to maintain a blistering average speed of 170,000 kilometers per hour. Earth is farther out, so it requires less speed to balance that weaker pull, averaging about 100,000 kilometers per hour. The rules are perfectly consistent here, guys. Proximity dictates gravity, and gravity dictates speed. Let's move to the 1800s and see how this builds into an incredible piece of history. This cosmic rulebook was about to be put to the ultimate test. In 1781, we discovered the planet Uranus. Fast forward 40 years to 1821, and a French scientist named Alexis Bouvard sat down and used the exact rules of gravity we've just been talking about to calculate exactly where Uranus should be in the sky on any given night. But that is exactly when the mystery began. Because when astronomers actually looked through their telescopes, Uranus was straight up misbehaving. The actual real-world observations didn't match Bouvard's predictions at all. The planet was inexplicably moving further away from the sun at these regular, repeating intervals. This was a huge crisis. I mean, was the math wrong? Was our entire understanding of gravity broken? Well, no. They eventually realized something else had to be out there. An unseen source of gravity was lurking in the dark, actively tugging on Uranus. So, the crucial point here is how beautifully the scientific method played out to solve this. First, they observed Uranus moving weirdly, completely contradicting the math. But instead of panicking and throwing out the rulebook, they trusted gravity. They realized if Uranus was being pulled off course, there had to be another massive planet out there doing the pulling. They used math to predict the exact location of this ghost planet, and in 1846, they finally pointed their telescopes right at that spot. And boom, there it was. They found Neptune. They didn't just stumble upon it by randomly scanning the night sky. They literally discovered it using pure mathematics and the strict laws of gravity. As the historical records note, Neptune was very close to exactly where they predicted it would be. And just think about how wild that is for a second. Neptune is 30 times further from the sun than Earth is, and its mass is 17 times greater than Earth's. Yet, even at that unimaginable distance, the sun's gravity is still strong enough to reach out and hold this massive world perfectly in orbit. It's an absolute triumph of science. It proves that the rules we cover today aren't just abstract theories, they are the reliable, predictable mechanics of our entire universe. From the crushing 270 newtons per kilogram of the sun's gravity to the frictionless vacuum that lets objects travel at hundreds of thousands of kilometers an hour, the math just works. And honestly, it leaves us with one final, pretty thrilling thought. If the invisible rules of gravity allowed us to mathematically predict and find Neptune, what the heck else is currently tugging on the edges of our solar system, just waiting in the dark to be discovered? Thanks so much for joining me for this explainer. Keep wondering, and I'll see you next time.